In the early 1600s, the first astronomical telescope was created by Galileo Galilei in Italy. As technology advances, humans have successfully found a better way to explore the universe today. It is the invention of the largest machine in the world, the Large Hadron Collider at CERN. This colossal machine, stretching over 27 kilometers, hidden deep below the Switzerland and French border, is not just a massive tunnel. It's a portal to the secrets of the universe. At its core, the LHC is like a giant racetrack for tiny particles called protons. Picture it like this. Imagine the LHC as a colossal tunnel with two lanes running in opposite directions. Inside these lanes, scientists send protons, particles smaller than atoms, whizzing around at speeds close to the blink of an eye. These protons are so small that if you could shrink yourself down to their size, you'd be smaller than a grain of sand in a vast desert. But here's where the magic truly happens. It's not just a matter of firing a few protons at each other. No, scientists at CERN unleash an astonishing 100 billion protons in each direction, creating a collision course of epic proportions. And you won't believe how many of these tiny particles actually collide. On average, out of the staggering 100 billion protons hurtling towards each other, only about 50 or 60 of them manage to collide. To put this into perspective, imagine standing in the midst of a bustling city with billions of people rushing past you. Now imagine trying to spot just 50 or 60 individuals out of that massive crowd. It's an incredibly tiny fraction, yet each collision holds the potential to unlock profound secrets about the universe. This remarkable feat is repeated over and over again, with scientists observing these collisions a mind-boggling 30 million times per second. With approximately 3,000 bunches of protons hurtling through the LHC, each containing over 100 billion particles, the result is an astounding 1 billion collisions per second inside this massive machine. These collisions are sufficiently violent that they are expected to briefly create conditions similar to those obtaining countless aeons ago, not long after the Big Bang, when the entire universe was still inconceivably small. It was smaller than a proton for quite some time, seemingly. Still, with all the stuff that nowadays makes up all the supra-enormity of space and galaxies and so forth packed in somehow. Naturally, some extremely strange phenomena are to be expected when one mangles the very fabric of space-time itself in this fashion. Various eccentric nutballs have claimed that this would doom humanity in one fashion or another, perhaps converting the entire Earth, everything on it, and possibly the rest of the universe too, into strangelay soup, monopole mulligatawny, or some other sort of frightful subparticulate blancmange or custard. It has also been suggested that cack-handed boffins at the LHC might inadvertently call into being a miniature black hole and carelessly drop this into the center of the Earth, rather irritatingly causing the planet to implode. It's certainly to be hoped that the button marked "Call Black Hole into Being" on the control board has some kind of flip-down cover over it. Evidently, these critics were wrong. We're still here in 2024, and though it can sometimes feel like we're living in a hellscape, we are, at least for the moment, still a pre-apocalyptic society. In fact, the LHC ran successfully at the headquarters of the European Council for Nuclear Research for several years before shutting down for updates in 2018. In that time, the particle accelerator facilitated some of the biggest international science collaborations the world has ever seen, resulting in the discovery of an elementary particle named the Higgs boson, a certified big deal. There's a reason it's nicknamed the God particle. But now, doomsday fears are rising once again, as the Large Hadron Collider is springing back to life to continue Run 3 operations at the energy frontier, a new period of data-taking that see it create collisions at unprecedented energy levels. This time, it's not mere black holes that people are anticipating either. Some boffins have speculated that black holes might alternatively act as space warp wormhole portals into alternate universes, or something. This would seem to chime with the remarks of Sergio Bertolucci, Director for Research and Scientific Computing at CERN. Out of this door might come something, or we might send something through it. In fact, the possibility of creating a black hole in a lab is a goal that scientists are actively pursuing, one that could allow researchers to answer many fundamental questions about quantum mechanics and the nature of gravity. A black hole typically forms when a star much more massive than our Sun dies. While the outer layers of such a star explode outward in a spectacular supernova, its core crumples inward, pressing down toward its central point with so much power that no known force in the universe can stop it. This results in a subatomic spot of unimaginable mass and density, whose gravity is so strong that even something traveling at the speed of light couldn't move fast enough to escape its clutches. These kinds of black holes are common throughout the universe. Of course, as long as something doesn't get too near a black hole, it's safe. Only within a spherical boundary surrounding the black hole known as the event horizon would a person or object get pulled inexorably inward. Enormous black holes have a big event horizon, with a diameter of millions of kilometers, whereas smaller ones have more minute event horizons, extending just tens of kilometers across. Fears about the LHC creating a black hole originated with the fact that in Einstein's special theory of relativity, mass and energy are interchangeable, hence the famous equation E equals mc squared, where c is the speed of light. Because a supercollider slams together protons at unbelievable velocities, nearing the speed of light, and energies, all sorts of strange and exotic particles can pop out, potentially including a black hole. But creating a black hole with even a microscopic event horizon would require billions of times more energy than the LHC is able to produce. And even if it could produce such a black hole, that object would quickly lose energy and dissipate in the blink of an eye. However, there are a number of theories that predict the existence of extra dimensions. Not merely the three spatial and one time dimension we know to be present in our four-dimensional spacetime, but at least one additional spatial dimension that exists in our universe. While we can't quite access those dimensions at the energies we've probed, it's conceivable that at scales that are smaller than those we've examined, which corresponds to higher energies, these extra dimensions exist. And if these extra dimensions exist, one theoretical possibility is that it might be possible to create black holes. And over the years, scientists have looked into the possibility that black holes could be wormholes to other galaxies. They may even be, as some have suggested, a path to another universe. Such an idea has been floating around for some time. Albert Einstein teamed up with Nathan Rosen to theorize bridges that connect two different points in space-time in 1935. Fresh ground in the 1980s, when physicist Kip Thorne, one of the world's leading experts on the astrophysical implications of Einstein's general theory of relativity, raised a discussion about whether objects could physically travel through them. Indeed, Thorne, who lent his expert advice to the production team for the Hollywood movie Interstellar, wrote, "We see no objects in our universe that could become wormholes as they age," in his book, The Science of Interstellar. In the words of Thorne, journeys through these theoretical tunnels would most likely remain science fiction, and there is certainly no firm evidence that a black hole could allow for such a passage. But the problem is that we can't get up close to see for ourselves, why we can't even take photographs of anything that takes place inside a black hole. If light cannot escape their immense gravity, then nothing can be snapped by a camera. As it stands, theory suggests that anything which goes beyond the event horizon is simply added to the black hole, and, what's more, because time distorts close to this boundary, this will appear to take place incredibly slowly, so answers won't be quickly forthcoming. As Douglas Finkbeiner, professor of astronomy and physics at Harvard University, said, "I think the standard story is that they lead to the end of time. An observer far away will not see their astronaut friend fall into the black hole. They'll just get redder and fainter as they approach the event horizon as a result of gravitational red shift. but the friend falls right in, to a place beyond forever, whatever that means. While opening a portal to another dimension is still just speculation, we know this beast of a machine became the battleground for the Higgs boson hunt. Often called the God particle, the Higgs boson is a tiny particle that stirred up a lot of excitement, not just among physicists but everyday folks too. It's like the missing piece in a giant universal puzzle, helping us grasp why things have weight. Yet finding it has been as tricky as locating a needle in a haystack, a real tough challenge in the world of physics. Imagine you're at a lively party. Some guests keep to themselves. Let's call them introverts. Others mingle freely, always found in the thick of things, are extroverts. Believe it or not, subatomic particles behave similarly. In the particle world, our loners are fermions. They're particles like electrons, protons, and neutrons, and they prefer their own space. Then we have the life of the party, bosons. They love being together, even in the same exact spot. This trait lets them carry forces, like how photons carry the electromagnetic force, which is why magnets stick to your fridge. But there's a super elusive boson named Higgs boson. What's the deal with this one? Why does it have a cool nickname, and why are scientists obsessed with it? Back in the 1960s, while moon landing plans were in full swing and music was triggering a revolution, physicist Peter Higgs was quietly upending physics with a bold new idea. Picture a puzzle. This was the standard model of particle physics, our best guess at how particles and forces work. But something was missing. Why do particles have mass? This is where Higgs steps in. He suggested an invisible field, the Higgs field, that spread everywhere like an endless ocean. Particles are like swimmers in this ocean. Some, like light particles, zip through effortlessly and are massless. Others struggle against the water, which gives them mass. The Higgs boson is like a wave in this cosmic ocean, caused by particles interacting with the field. So, Higgs boson was the missing piece that explained why particles have mass. But a theory isn't worth much without proof, right? Thus began the epic quest to find the Higgs boson, leading to one of the biggest scientific experiments ever. And the LHC, as told, is like a supercharged racetrack that speeds up protons, particles inside every atom, to nearly light speed. These protons then crash into each other, breaking apart into tinier particles and mimicking conditions right after the Big Bang. But how do you spot something a billion times tinier than an atom that only lasts a fraction of a second? This is where the LHC's brilliance comes in. When a Higgs boson is made in a proton crash, it quickly decays into other particles, leaving a unique signature. Scientists hunted for these signatures to confirm the Higgs boson's existence. Finding it was no easy task. Imagine locating a unique grain of sand on a beach or a needle in a haystack as big as Mount Everest. But on July 4th, 2012, the hard work of thousands of scientists paid off when CERN announced they'd found a particle consistent with the Higgs boson. The God particle was now more than just a theory. It was real. Finding the Higgs boson was a massive feat. First, the Higgs boson validates the standard model of particle physics. This model needed the Higgs mechanism, which gives particles their mass, to be complete. The Higgs boson was this missing piece, a huge win for human intellect and our quest to understand the universe. Second, it's all about mass. The Higgs field, linked with the Higgs boson, is what makes particles heavy. Without it, particles would move at light speed and our universe wouldn't exist. No stars, no planets, no life. So, knowing the Higgs boson is knowing the building blocks of reality. Third, finding the Higgs boson opens doors to new discoveries. For example, it could help us get dark matter, the unseen stuff making up 27% of the universe, or even how the universe began. But while the Higgs boson is our ticket to understanding the wondrous universe we live in, Stephen Hawking, the famous theoretical physicist, has warned that the particle could one day be responsible for the destruction of the known universe. Notably, Hawking is not the only scientist who thinks so. The theory of a Higgs boson doomsday, where a quantum fluctuation creates a vacuum bubble that expands through space and wipes out the universe, has existed for a while. However, scientists don't think it could happen anytime soon. As Joseph Liken, a theoretical physicist at the Fermi National Accelerator Laboratory in Batavia, Illinois, said during his lecture at the SETI Institute, "Most likely, it will take 10 to the 100 years, A1 followed by 100 zeros, for this to happen. So probably you shouldn't sell your house and you should continue to pay your taxes. On the other hand, it may already happened, and the bubble might be on its way here now. And you won't know, because it's going at the speed of light, so there's not going to be any warning." Scientists discovered this when they made countless calculations to measure the particle's mass. According to estimates, the Higgs boson is about 126 billion electron volts, or about 126 times the mass of a proton. This turns out to be the precise mass needed to keep the universe on the brink of instability. But physicists say the delicate state will eventually collapse and the universe will become unstable. That conclusion involves the Higgs field. The Higgs field emerged at the birth of the universe and has acted as its own source of energy since then. Physicists believe the Higgs field may be slowly changing as it tries to find an optimal balance of field strength and energy required to maintain that strength. To understand how the Higgs field works, let's imagine you've got a ball at the very top of a big mountain peak, where if you move any distance in any direction, you're going to roll down the mountain. Any direction you begin rolling in is going to take you down towards a valley, but in some directions, the valleys are at lower or higher elevations than others. The direction your ball begins rolling, at least to start, is totally random, and so which valley you land in is going to be random as well. Unless you're very, very lucky, like landing in the winning slot in the ultimate game of Plinko, you're not going to wind up in the lowest possible valley, just the lowest one in the vicinity of the direction you initially chose. There's a strong possibility that the potential that describes the Higgs field looks a lot like this mountainous picture, and that the universe we inhabit, complete with the particle masses we observe, currently lives in one of these metastable valleys, one where the elevation, the value of the potential, is lower than all the surrounding regions, but not necessarily in the lowest overall state. In the picture we just painted with a ball rolling down a mountain slope, it will remain wherever it came to rest, because that's a classical system. But the Higgs field, and the universe in general, is a quantum system, which means that there's a small, finite, but non-zero probability that at any given time, the value of the Higgs field in our universe could quantum tunnel into a lower, more stable valley. That's the situation that Hawking is describing, and even though the probability of that occurring is very, very small, it is possible. And if this is, in fact, how our universe looks, it could literally happen at any given time. But is this the situation that does, in fact, describe our universe? What would happen to our universe if this tunneling to a lower energy state happened? Would it, in fact, be destroyed? Or would the changes that occur leave the universe intact, if only a little different than before? First off, it's a very contentious claim to say that the Higgs field has settled into a metastable state. While our best calculations say that the Higgs may become unstable at energies in excess of 10 to the 11th giga-electron volts, where a giga-electron volt is the amount of energy required to accelerate an electron from rest to a potential of 1 billion volts. Those are based on mass measurements of bosons, such as the Higgs, W boson, as well as the top quark, that still have significant uncertainties on them. Within the measurement uncertainty, the Higgs may yet turn out to be truly stable, meaning that we already may be in the lowest part of the valley. In addition, There are strong reasons to believe that the theory of asymptotic safety describes gravity, and therefore predicts a value for the Higgs mass that's perfectly stable and consistent with what we observe. If this is the case, then the Higgs isn't metastable, and the whole issue is moot. Second off, what would happen if this scenario were true, and some place in the universe made the transition to a more stable state? It would be most likely to happen not here on Earth, nor even in our high-energy particle colliders, but near a supernova, hypernova, active galactic nucleus, or supermassive black hole. It's the highest energy locations in the universe that are far more likely to undergo this quantum transition, where energies of approximately 10 to the 10th giga-electron volts and above are routinely achieved. For comparison, the highest energies achieved at the LHC are only around 10 to the 4th giga-electron volts, which means the odds of the transition happening by us are far lower. If the transition happened, the laws of physics would instantly change, with properties like the masses of particles, the strength of interactions, and the sizes of atoms changing instantaneously, where the Higgs field achieved this lower value. In addition, the lower value of the Higgs field would begin to take over the universe, with the transition propagating outward at the speed of light. This is both good and bad for us. It's bad because we'd never be able to see it coming. All the observable signals of the universe propagate no faster than the speed of light in vacuum, and so if the transition is propagating at that speed, we'd have no signal of it before it was on top of us. But it's also good, because the universe is accelerating in its expansion, meaning that, for 97% of the observable universe, a signal propagating at the speed of light will never reach us. So even if the transition happens somewhere in our universe, it's unlikely to affect us. And finally, if the universe turns out to be metastable, but only very slightly so, the changes in the laws of physics, the sizes of atoms, etc., might be so small that, although they'll be perceptible to physicists experimenting with them and probing the laws and properties to high precision, it might not destroy anything, but simply impart to them slightly different properties. So although this might be a possible way to destroy the universe, it's very unlikely. It might not be a possible way to destroy it. It might not even affect us if it does happen, and it's also something we have really no control over. But if you wanted to destroy the universe, relying on the Higgs is a fool's game. The smart money is to bet on cosmic inflation and to remember that the only reason our universe exists as it does is because inflation came to an end. If we could reactivate it, if we could create a new inflationary epoch, the ultra-rapid expansion of the universe that would ensue, and the incredibly intense energy intrinsic to space itself, would push apart not only the galaxies, but solar systems, people, cells, molecules, and even individual atoms. So how would that work? Inflation was the state that existed prior to our universe being filled with matter and radiation. Prior to our universe being in a hot, dense, expanding and cooling state, prior to the Big Bang. All the energy that exploded into the matter and radiation at the moment of the Big Bang came from somewhere. And inflation tells us that the where it came from was from energy intrinsic to space itself. The energy intrinsic to space itself now is much lower, at least a factor of 10 to the 27th, and possibly as much as 10 to the 31st times smaller than it was during inflation. But if we can achieve those incredibly high energies again, and do keep in mind that these are higher energies by far than any known energy source in the universe achieves, we could perhaps restore a state of inflation to our universe, destroying everything within it and hitting the cosmic reset button. All we'd need to do, if we wanted to try, is create ultra-high energy collisions with an energy of between 10 to the 15th and 10 to the 19th giga-electron volts, and hope that the transition to an inflationary state occurs once again. Although this isn't right now practically achievable with current technology, we know exactly what we'd need to do to make this happen. You see, we know how to accelerate particle-antiparticle pairs in opposite directions in a circle. And we know that the bigger the magnetic field and the larger the radius of the circle, the faster we can get the particles to go and the higher energies we can achieve. The old Tevatron at Fermilab achieved energies of about 10 to the third gigaelectron volts per particle, resulting in up to 2 times 10 to the third gigaelectron volts, released during a particle-antiparticle collision operating under this principle. And the LHC is poised to reach about 7 times 10 to the third gigaelectron volts per particle, giving us up to 1.4 times 10 to the fourth gigaelectron volts per collision. Ignoring the phenomenon of synchrotron radiation, which we can compensate for by building a larger radius ring anyway, the formula for a particle's approximate energy is given by an incredibly simple relation. Take the strength of the maximum magnetic field in Tesla, multiply by the radius of the ring in kilometers, and divide by 4. That is the maximum energy of your particle in gigaelectron volt. So if we want to reach 10 to the 19th gigaelectron volts per particle, the approximate Planck energy, all we'd need to do is build a machine identical to the LHC in all ways, except instead of a ring that's about 4.1 kilometer in radius, we'd need one that was 5.9 by 10 to the 14th kilometer in radius. Yes, that's very, very big, but it isn't impossibly big. We're not talking about building something the size of the universe, but rather about building something only about 4 million times the size of Earth's orbit around the Sun. And that's being very conservative, assuming it takes those incredibly high energies to restore inflation. It could happen at a factor of 1,000 or even 10,000 less in energy, which means that much smaller of a ring. Alternatively, we could achieve practical improvements in electromagnet technology, reducing the radius of a ring even further. So cheer up. Destroying the entire universe and pushing the cosmic reset button isn't something we have to wait around for, and isn't even something that's totally out of our control. We have the science today to make it happen. The only challenge is the materials, the engineering, and the money. Put those all together, and the end of the universe, and the birth of an entire new one, is yours. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve.